So in this video we're going to discuss the inclusion-exclusion principle, which is a generalization of a formula that we derived in the previous video. In the previous, well, not in the previous video, in the video, the previous video to the previous video. So the video before the previous video. So in the video before the previous video, we derived the result that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A union B. And basically what you can now do is you can generalize this. So we want to take the probability of an arbitrary union, n is equal to 1 to infinity, well, not to infinity, n is equal to 1 up to big N, we'll say, of an, where these are all events. And the inclusion-exclusion principle is basically a formula for this. And it basically says that it's the sum from n is equal to 1 to big N of the probability of an minus the sum from, oh dear, I is less than j now, of the probability of AI intersect AJ, then we'll have plus the probability, the summation of I is less than j, less than, not less than or equal to, less than k, of the probability of AI intersection AJ intersection AK, and then you go on all the way to the final term, which will be plus minus 1 to the n plus 1 of the probability of A1 intersection A2 intersection all the way up to intersection A big N. Okay, so I'm going to give you an example of this formula for, let's say, big N is equal to 3. The way that you would properly prove this is you would do an induction. I've never seen that proof before, so instead what I'm going to do is I'm going to give you an intuitive version of this. The problem is it won't be rigorous, because it won't just use the axioms of a probability space. The proof that I give you won't apply for all probability spaces. It will apply under certain conditions, but this formula applies for anything, for any probability space, and you can prove it by induction from here, I'm assured. I should look up the proof and do a video on it. So for n is equal to 3, what would you do? In fact, we might have a go at the end of the video. I'll probably fail, but we might have a go at trying to prove it by induction. But I'm going to show you the intuitive proof first. And firstly, I'm just going to show you that it works for n is equal to 3. So the probability of n is equal to 1 to 3 of an. So we could rewrite that as the probability of A1 union A2 union A3. And we're saying that it's equal to the summation from n is equal to 1 to 3, which we could rewrite as probability of A1 plus the probability of A2 plus the probability of A3. Then we have to subtract off these intersections for I is less than j. So let I equal 1, then j could equal 2 or j could equal 3. So we'll do plus the probability of A1, sorry, minus, it's got a minus there, A1 intersection A2. Now we'll do minus the probability of A1 intersection A3. And then move I up, it's now 2, the only number that j could be is 3, so minus the probability of A2 minus A3, intersection A3 rather. Okay, and then the final term will be this huge great thing here, which will have a plus, because 3 goes in here, 4 minus 1 to the power of 4 is 1, plus the probability of A1 intersection A2 intersection A3. Now, how would we derive that from here? Well, what we do from this result up here, well, what we do, and this would be the inductive step, you'd say, assume this applies for n, and then show, using this result up here that we know is true, that it's then true for n is equal to 1. And the way you do that is, if you wanted to, you'd say that the probability of A1 union A2 union A3 is equal to the probability of A1 union A2 and then union A3. So we could rewrite this with this formula up here as the probability of A1 union A2 plus the probability of A3 minus the probability of A1 union A2 intersection A3, and then what you would have to do is you'd use the formula that we had before to write this out, and then you'd have to somehow find a way of computing this. So let's try and do that let's try and do that since we've started now. So we'd replace the probability of A1 union A2 with the probability of A1 plus the probability of A2. So we now have all of those plus the probability of A3, so that's looking hopeful. And we're going to have to subtract off the probability of A1 intersection A2. And we've also got this subtracted off here, minus the probability of A1 union A2 intersection A3. And now we're going to have to pull some clever trick that I'm going to have to spot. So we know something. We know that this distributes, that it's a basic axiom of set theory that that the union distributes over intersection. So if I union two sets together and then I intersect that union with A3, it's basically saying what's in A1 plus what's in A2, and then it has to also be in A3. We're saying restrict our attention now to only the things that were in here that were in A3. So if we just restricted all the things that were in A1 that were in A3, and restricted all the things in A2 that were in A3, and then union them together, that's the same answer. So we can rewrite this out as the probability of A1 intersection A3 union A2 intersection A3, and that's called the fact that intersection distributes over union. So it's similar to multiplication here and addition here. It's obeying the same property, the distributive property. And this is on a really weird angle. Let me just sort this angle out. We'll have it more like that. Okay, need another piece of paper. Right, okay, so where were we? We were trying to prove this. So we can now apply. I'm just going to follow my nose here. I haven't seen this before, but I would imagine that what you have to do is apply the formula we already know again. So imagine this is now one set here, and this is one set here. We're unioning them together. So I can rewrite this as the probability of A1 intersection A3 plus the probability of A2 intersection A3 minus the probability of A1 intersection A3 intersection A2 intersection A3. Well, that's brilliant, because this is the same thing as the probability of A1 intersection A2 intersection A3. You're basically saying, get me what's in A1 and in A3 and in A2 and in A3. So all the elements that are in all three, so it's the same, you don't need the A3 there twice. Okay, so now I think we've done it. We had probability of A1 plus the probability of A2 plus the probability of A3. Oh no, we haven't. Something's gone horribly wrong here. Or has it? No, I think that's right. Yes, that looks right. So we've dealt with this bit here, and this is what this is here. So if we rewrite this whole thing here, which was the probability of A1 union A2 union A3, this thing that we had up here, and it's equal to all of this minus this, and it was minus this, but we've shown that that is the same as this thing over here. But all of that minus we're going to have to do because there was a minus sign here, and this was, we were just saying this bit here was equal to this, and that's equal to that. So we'll get is equal to the probability of A1 plus the probability of A2 plus the probability of A3 minus the probability of A1 intersection A2, which is up there. Then we've got minus this thing here, minus the probability of A1 intersection A3, and then minus the probability of A2 intersection A3, and then we'll get plus this whole intersection down here, the probability of A1 intersection A2 intersection A3. So that is a fully rigorous proof that works for any measure any probability space, that all of that works, and all we used were the basic Zermelo-Frenkel axioms of set theory, which we can assume are true. the intuitive picture of why that holds, and of course this is the picture on which the axioms of set theory is based, is that you have these three events here, or these three sets you can view them as, but of course events we are modelling as sets. This is A1, this is A2, and this is A3. And basically what we said is add up all of these. So you add up, the first step you did was you added up all of the separate things, but you overcounted quite a bit. So each of these bits that's just an intersection of two of them, you counted twice, so you need to subtract each one of those off. The problem is you can't just subtract these sort of leaf-shaped bits like this here. You have to subtract the whole intersection, which means you're subtracting off this bit here as well. So you're going to subtract that off 3 times. You added it on originally 3 times because you added it was in all 3 sets. So you added it on 3 times. You then subtracted it off 3 times when you subtracted off all the intersections to rectify the fact that you'd overcounted all the intersections. Therefore you have to add it back on 1 time, and that's the intuitive picture of why that result is true for 3. So to prove this for an arbitrary n, I'm firstly going to give you the intuitive picture in terms of the picture here, and then I might attempt to come up with a proof by induction. At least give you an outline of how I would approach trying to make a proof by induction. But as I said, I've never seen it before, so it will be rather on the spot. But considering how well that one went, I might just attempt it. But of course, you're going to have to make loads of these clever things, and I bet I won't be able to do it. Okay, so the intuitive picture, the intuitive view of the intuitive view of inclusion-exclusion. And the problem really is that this will only work when your where this proof is only valid when the set of events contains every unitary set. And what do I mean by that? I mean take every outcome in the sample space, which is this omega thing here. You take every element in the sample space, put it in its own set. That forms a subset of the whole sample space, and you put every single one of these sets into the set of events. And if that holds, then this proof is valid. If it doesn't hold, this proof is slightly less valid. But the result holds for all probability spaces and can be derived by a proof by induction. Okay, so the intuitive picture then. If you want the probability of this union, n is equal to 1 to big N of an, then it is equal to, let little x be an element of this big set, of this union rather. Then we can ask, where do I approach this? Okay, I could rewrite this as basically for every let me just write it out and then I'll explain why. Basically, if you union absolutely every not like that. If you take, I want to draw a picture to explain this. Okay, I'm going to draw a picture rather than just writing out the formula. Okay, so if you have your sets, you have A1, A2, and you have these arbitrary sets. Basically, in the whole great big union, which is all of them combined together, you have lots of little outcomes. The outcomes are in there. So let x be an element of this great big union of these sets. So let x be an outcome that is in the union of all the events, is in this event which is the union of all these events. Okay, basically I could write the probability of this great big union as the probability of the union of all of these singleton sets, basically, for all of the so basically take every outcome that's in this union. Its singleton set, by hypothesis up here, was an element of the events. So I could write this great big union as this union of all these sets containing all the singletons that were in the overall union. and that's completely valid. So take the union over x is an element of this union of the singleton sets, and then by property 2 these are all disjoint, therefore I could write this as the probability of each singleton. I could write it as the sum over x is an element of the union n is equal to 1 to big N of an of the probability of the singleton, so of the singleton set. So of course the probability is not a mapping from the sample space, so I shouldn't write probability of x. I should write the probability of the set containing x, because it's a mapping from the set of events rather than from the sample space. Okay, so that's valid, and basically that's important because now what I can say is for all basically what I can say is that all I need to do is go along and take every little outcome that's in your overall union, and you just need to add up its probability. But basically when you add up when you do it in the way that we are going to do it, you're going to overcount these points in here. So if x is an element of union n is equal to 1 to n, an, then what I can ask is how many times is it going to be counted, basically, when I it is an element of at least one of the AI's. I is equal to 1, 2, 3, all the way up to n. So it's in at least one of them. Call the set of AI's which x is in S. So S is equal to the set of AI's such that x is an element of AI. So put all of these sets that you're unioning together which contain x in this set. And so it's in at least one of them, so this isn't an empty set. And basically what I want to show you is that when you apply the inclusion-exclusion formula, it will be counted, this point, this outcome, will be counted once overall. And therefore, its probability will be counted once as well. So basically we are relying on property 2 here of the probability spaces, that when we add up things like, where's the formula? When we add up things like this, it contains a bunch of these singleton points, these outcomes, and that its overall probability is the sum of all the probabilities of the singletons. That's a very powerful thing that's true for any sample space such that the set of events, for any probability space such that the set of events contains all the singletons, but it's not true for an arbitrary probability space. Okay, so basically I just want to prove that x is counted once by this great big formula, and the way that you do that is it's going to be in, so we can take the modulus of this set S, and let's call that M, big M. So it's in M of these sets AI. Then in the first thing, its probability is going if we look at the formula here for the inclusion-exclusion principle, its probability is going to be counted M times, because it's going to be in M of these. Then what are we going to do? We're going to subtract off how many of these is it going to be in? Well, it's going to be in M choose 2, because that's the number of ways there are of choosing two sets to intersect from the sets that it's in. So it's only going to be in AI intersect AJ if it's in both AI and AJ. It's in M of these sets, so how many ways are there of choosing two sets from these M sets in S? It's M choose 2. We're then going to add on M choose 3 for this one here, well, the one that I haven't written out, for the next one along. Oh, sorry, we're looking at the not general formula, we're looking at, this is the general formula up here. So for the next one along, how many ways are there of selecting 3 sets which it's all in? Well, that's M choose 3, we're going to add that many of them on. We're then going to subtract off M choose 4, and it will go on all the way up to plus minus 1 to the n plus 1 of, it'll be m choose m. And we could write m choose 1 there. And basically, let's just expand that formula out. So that's how many times this probability of x is going to appear, basically, in the sum. Because what I want to stress again, and I don't think I've explained this well enough, is that each of these we could expand as probability of all of the outcomes that are in it. So in this set, AR intersect AJ, there are... this is the set here. You have a bunch of outcomes, and you could write this as the probability of each out of the set containing each outcome on its own, all added together. So in there, if x is an element in there, in that huge great sum, you'll somewhere have the probability of x. So we are working out in this overall huge great sum we do here, where we add up all of these probability of AI intersect AJs, how many times does probability of x appear? And basically, it's going to appear m choose 1 times in this, because it will be in all of the ones where you have probability of AI such that AI is an element of S, and then in here it will appear m choose 2, but you're subtracting it all off, so it's going to be this sum is the overall number of times it appears. So now let's expand this out. We could write this m minus m times m minus 1 over 2 factorial, plus m minus 1, m minus 2 over 2 factorial. Minus m minus 1, m minus 2, m minus 3 over 3 factorial. Oh, sorry, no, that's over 4 factorial, and that's over 3 factorial back there. And you go all the way up to plus negative 1 to the n plus 1 of, where did I get, n plus 1, that's fine, of m choose m. Is that right? Something's gone up here. Okay, this is fine, but I'm confused about that. Where did I get that from? Oh no, that's fine. So you sum over the total number of unions you're going to get. Oh, you're going to stop. I've made a silly blunder here. It's in m sets, so this is going to be 0, because if m is less than n, it can't possibly be in A1, so you'll stop somewhere. I've made a terrible error here. You don't go up to this final term here, because it won't be in that term. Eventually, you will stop at the term where you have the probability of A1, AI intersect AJ intersect AK, and you're intersecting m sets, so let's say index m. When you're intersecting m sets, that will be the final point at which you can actually have a set that contains x. After that, you'll be intersecting it with a set that isn't in S. You'll be forced to intersect it with a set that doesn't contain S, because you've run out of sets that do contain x, so you won't be counting x. So you'll go up to there, and we just now need to work out what the sign is in front of here. So this was m choose 1, this was m choose 2, this was m choose 3, so in front of all the odd numbers you've got a plus, and in front of all the even numbers you've got a minus, so it should be minus m plus 1, I think, because if m is odd, then that will give an even number, so it will give a positive one, and if m is even, that will give a negative number, so that's fine. Okay, and basically now we're going to make an observation, which is that if you look at the binomial expansion of 1 minus x to the m, what is it? Well, it's going to be equal to 1 minus x plus m, oh sorry, no, minus mx there, minus mx, plus m minus 1 x squared over 2 factorial, all the way up to plus, it will be negative 1 to the odd powers have this, so negative 1 to the m, x to the m of, and it would be m choose m, so that will go down to 1. So that's looking pretty similar to what we've got here, except that the negative signs are in the wrong place, and we've got this 1 over here. So if we put in x, well, firstly, let's just consider if we take minus 1 minus x of m, that's equal to negative 1 plus mx minus m minus 1 x squared over 2 factorial, all the way up to plus dot dot dot, all the way up to minus 1 to the m x to the m. So we could write that as m plus 1 there. Okay, and then if we just move this paper up, now consider 1 minus x to the m, and we get that that is mx, so this goes basically, you add the 1 and that cancels and you get 0. mx minus m minus 1 x squared over 2 factorial, all the way up to plus dot 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 plus minus 1 to the m plus 1 x to the m. And now just substitute in x is equal to 1, and you will get this great big term we had up here. You'll get m minus minus 1, and it will all work out. And what do you get on this side? You get 1 minus 1 to the m. Well, 1 minus 1 is 0, so you just get 1 on this side is equal to m minus m minus 1 over 2 factorial plus all the way up to minus 1 to the m plus 1 x to the m. So there is your proof of the inclusion-exclusion formula, providing, as I say, that these unitary sets, these sets containing just one element, were all elements of the set of events and therefore had an ascribed probability. And then you can just apply axiom 2 of a probability space to say that I could rewrite any event in terms of the summation of the probabilities of these unitary sets. Okay, do I feel up to trying to prove it by induction? We'll have a go just to show you. I don't think we'll succeed, but it might pique your interest and you can then go and look it up online. Okay, so let's attempt proof by induction. So we basically assume that this formula holds true. That's the way we do an induction. We assume it's true. We know it's true for n is equal to 2. We also know it's equal for n is equal to 3. So we have our basis step. We now take the inductive step. We say, well, we take the assumptive step first. We say this is true for n. Let's prove that it's now true for n plus 1. So if I take the probability of the union n is equal to 1 to n plus 1 of an, then I could rewrite that as the probability of the union n is equal to 1 to big N of an, and then I could write it union an plus 1, couldn't I? And therefore I could expand that with our basic formula that we know from up here. I could rewrite that as the probability of union n is equal to 1 to n plus the probability of an plus 1, big N plus 1 rather, minus the probability of this great big union, n is equal to 1 to big N of an intersection an plus 1. And I'm hoping this is just going to sort of, if I just follow my nose, this is going to come out nicely. Okay, so what I can do is I can use the inclusion-exclusion formula, which I have assumed is true for up to n, big N. I don't know it's true for n plus 1, but I don't need it to be true for n plus 1. So I can write that out in terms of the inclusion-exclusion formula. an plus 1 is fine, and then I need to apply, as I say, this distributive property of intersection over union, and hopefully something nice will happen. Okay, so I apply the inclusion-exclusion formula then, and I get that this is the sum over n is equal to 1 to big N of the probability of a little n minus the sum from I is less than j of the probability of ai intersect aj plus the summation I is less than j is less than k of the probability of ai intersect aj intersect ak. And it goes on and on and on, all the way down to plus minus 1 to the n plus 1, the probability of a1 intersect a2 intersect all the way up to intersect an. Okay, so that's good. Then we add on, up here, we can add it on up to here. We add on the probability of an plus 1. So I might as well just stick an n plus 1 up there. So that has taken care of that term and that term. Now I'm going to rewrite this term, which is the probability of, we rewrite it as the union n is equal to 1 to big N of an intersect an plus 1. And now I can see what you're going to have to do. You're going to have to apply the inclusion-exclusion principle for that, and this is going to get... Oh. Okay, so we'll keep going and see where we get. I'm not going to rewrite all of this bit out. Instead, I'm just going to rewrite this term here now. Using the inclusion-exclusion principle, I can say that I know that the inclusion-exclusion principle is true for the union of up to n sets. So I apply it for this using my assumptive step, and I get that it's the summation of n is equal to 1 of big N of the probability of n intersect a big N plus 1. Then I will get minus the summation I is less than, not less than or equal, less than j of the probability of a, now how should I do that, ai intersect an plus 1, and then it will be intersect aj intersect an big N plus 1. Okay, this is getting messy. And then I won't put the third term, well actually I will put the third term so we know where we're going. The sum I is less than j, the less than k of, oh this is going to be messy, ai intersect an big N plus 1 intersect aj intersect a big N plus 1 intersect ak intersect an plus 1. So obviously you can see that some nice cancelling is going to happen here because there's no point intersecting a big N plus 1 3 times. And then we're going to get plus minus 1 to the big N plus 1, the probability of a1 intersect a big N plus 1 intersect a2 intersect big N plus 1 intersect all the way up to a big N intersect a big N plus 1. Okay, so the first thing I'm going to do is I'm going to say drop intersecting it these multiple times. You don't need to bother doing that. What else can I say? Oh, because we've got a negative sign there, we can stick negative signs in front of that, a negative sign in front of that, a negative sign in front of that, and drop the plus 1 there. Okay, that's good. Okay. Oh no, actually, maybe to make it more intuitive, what I should have done is add another one onto there. Why am I doing that? Because I know the inclusion-exclusion principle is big M plus 1. So if I put in big M plus 1 here, I get M plus 2. So to make the formula look better, it would be nice if I put M plus 2 there rather than just M. But that doesn't, that's, you know, so that I can see more easily how this is going to become the formula I know and love. Okay, so I'm hoping now that if you just put all of these in with these, that it's all just going to work beautifully. So let's have a look. We are intersecting here. It must work. Okay, so let's try and prove that it works. Let's try and get an understanding for why all of this is going to go together to make the inclusion-exclusion formula. I want to get the whole thing in view for you. Right, okay, so here we intersect all of the possible combinations that you can get for n such that I is less than j. Here we intersect all of these with an plus 1. Is that going to give you every possible intersection you could have where I is less than j and you let them both go up to n plus 1? Yes, it is. Why? So, ooh, I don't think it, no, how can I explain that? So what we have is we have n sets originally. We have n sets. So we have, let's draw it out, A1, we have A2, we have all the way up to AN, and I am picking any two of these and intersecting them. Okay, and order doesn't matter, so A1 intersect A3 is the same as A3 intersect A1, and I only want it to appear once, which is why I'm doing this summation I is less than j. Here, I'm saying take each one of these and intersect it with the final one, which is am plus 1, and I'm saying that if I take every possible combination here and I add on all the possible combinations of this one intersect this one, intersect this one, intersect each one with this, then that somehow gets all of them for m plus 1. Well, that's true, it has to be, because basically which intersection of two things is not on there? Any intersection either has to be between two sets that are in here, or it has to be between one of the sets in here and one of the sets in here. That's just logic, and therefore this must contain every possible intersection you can possibly have. So that, along with that, makes the correct term for the inclusion-exclusion formula for m plus 1. Then we will go to this bit here and add it on to here. And again, this is going to give you every single one where you don't intersect it with am plus 1. And then this is going to give you pick any two from the original two you have here and intersect it with am plus 1, which again is the only, those that include every possible intersection of three things that you can have. And it's going to work the same throughout the whole thing. And this, basically, this what I've written down here, can be reduced into the inclusion-exclusion formula for m plus 1. So that's your proof by induction there, basically. It's messy, I know, but basically what that shows is that this result does hold for general probability space, because now I did not need, nowhere in this proof did I need every singleton, every set containing a single outcome to be an event, which obviously isn't true in a general probability space. That isn't one of the axioms of a probability space. That's true in finite, well, it doesn't have to be, but in most finite probability spaces, you know, you can ascribe a probability. So if you roll the dice, you can ascribe a probability to the outcome that you get a 1, a 2, or a 3, or a 4. All of those singleton sets have an ascribed probability, but as I say, the example I keep coming back to is this interval 0, 1. You can't ascribe a probability to the outcome that you get exactly 0.5. So that is the inclusion-exclusion principle. In the next video we will use the inclusion-exclusion principle to solve the matching problem.